Everybody. So this is an interesting problem that I found it in a section on area between curves, and it does use area between curves, but I think it's just kind of a good general example of problem solving when it's not a kind of problem you've seen before, right? And one of the jobs we want to be accomplishing while we're going through calculus is we're preparing to be mathematicians or scientists, most of us, and that means we're going to be trying to solve problems that no one's ever showed us how to do before. And so we need to know what to do when we don't just go, oh, I've seen this. I just, replace these numbers and do it this way, follow this set of rules, right? That's not very interesting for a scientist to study things that we already know how to solve. What we want to study are things we don't know how to solve. And so we need to kind of develop a set of skills around problem solving. I think this problem is a good example of that. So let's go through it. Statement is there's a line through the origin that divides the region bounded by the parabola y equals mx minus nx squared and the x-axis into two regions with equal area. What is the slope of that line? So first of all, m and n, I'm just letting them represent some coefficients. And I think I should have put this in. M and n are going to be positive. It just makes that's how I presented the problem. I was putting in various versions of this, but they were always positive, just to make it a little bit simpler to approach. So when we come across something like this, a first thing we might want to do is figure out how to understand the problem, right? So there's kind of a lot going on, and so it might make sense to try to figure out exactly what the problem's asking us. So the first thing I might do is look at this function y equals mx minus nx squared and get a picture of it. So I can picture this region they're talking about. So I'm going to name this thing. Instead of y, I want to give it a name so it's easier to distinguish it from other functions that might show up in the problem. And let's graph this thing. It's a parabola. It's facing down. The x squared term, the quadratic term, has a negative coefficient. Let's just find its zeros. So we want to solve where does f of x equal 0. So this is a simple enough problem to do. Mx minus nx squared is 0. X times m minus n x equals 0. So we see that x equals 0 or x equals m over n. Okay, those are our two zeros. So I should be able to graph this quickly. I'm not worrying at this point about making it especially perfect, my graph. I'm just going to draw a couple of axes and then sketch my graph. I'll use red for this. And I'm only going to draw the relevant portion. So here's my two x-intercepts, right? There's one at 0, 0. There's one at m over n, 0. And it's a downward facing parabola, so I know, oops, that's not good. Right, something like that. Okay, so it's not a perfect drawing, but it should hopefully be good enough. Maybe I'll thicken this line a little bit, make it a little easier to see, I hope, so I don't screw it up. Okay, so there's our parabola. We've also got, oh, and so this is the region we're talking about, okay? So I'm just gonna label this as f of x. That's the region we're talking about, the part trapped between this parabola and the x-axis. And then there is a line through the origin. So let's draw that. And this line splits this region into two sections with equal area. So let's try to eyeball that. So I want a line through the origin. Let's Well, let's see what happens. How about something like, that's relatively close to being through the origin. Let's make this a different color. It's a little easier to distinguish. Okay, so the idea, again, it's not perfect, but imagine that these two areas that this thing has split it into are equal. And maybe I'll name those. Let's call this area 1 and this area 2, and I'll call the whole area area total. Okay. All right, so what we're trying to find is the equation, sorry, the slope of this line. Let's write down something, right? When there's something we want to find, for instance, the slope, it's always useful to name it. Okay, so this is another problem-solving strategy. Let's think about what we've discovered so far. We just tried to understand the problem, and one way to do that was drawing a picture. Like, so many problems lend themselves to drawing a picture. It's not always possible or useful, but it's almost always worth a try. And I would say in this case, it's almost impossible. I would have not been able to solve this without drawing a picture to understand what's happening. Another crucial step is naming things. In particular, among other things, naming the things you want to find, right? So I didn't have to name f of x, right? I named f of x, this parabola that was given, because I wanted to be able to distinguish it from other functions if they showed up. But if I'm looking for slope, I need to give that slope a name, because when this problem's done, whatever name I give it, I should have that equals some number, right? That's what this problem's asking for. And I could write slope over and over, but that seems cumbersome. So I'm gonna name the slope. And in fact, I'm just gonna give a name to this line. This is also a function, let's call it g of x. And a line through the origin is just gonna have the form, whatever that slope is, so I've called it m, times x. So now what we're trying to find is the value of m that splits this area in two, okay? So let's see. Now I've solved this, but I want to go through the process that, like, I know where the solution is, but when I started it, I didn't. So if you're staring at something like this and not sure where to go, one good strategy is, let's just start writing down things we know or gathering information. So this is a problem about area and about splitting this area in two. Let's just compute the area of this region, the entire region. So I'll call it area total. And let's, so the area total, the area under this parabola, this whole region, is going to be the integral from 0 to m over n of f of x, which is, of course, the integral from 0 to m over n of mx minus nx squared dx. So remember, m and n are just constants. So we can use our simple integral rules. The antiderivative of x is going to be x squared over 2. So we'll get m over 2 x squared minus n over 3 x cubed, evaluated from 0 to m over n. So let's see, we'll have m over 2 times m squared over n squared minus n over 3 times m cubed over, oh, there we go, n cubed. That's putting in the m over n, minus evaluating at 0, but it's quick to see putting in 0 just makes this whole thing 0. So now let's simplify a little bit. This is pretty ugly. We've got m cubed over 2n squared minus m cubed over 3n squared. In other words, we have half of m cubed over n squared minus a third of m cubed over n squared, which means we have a sixth of m cubed over n squared. Okay, so that is the total area. Okay, this is the total area. Let's keep this label here. Or I could also say this is area 1 plus area 2, right? As I've labeled it in the drawing. I don't know how I'm going to use this exactly yet, but this is certainly good information to have. So I'm just going to remind myself that this is important, give it a little box. All right, so let's go back to the problem. What else do we want? We want this line to split this thing in two. So another way we could say that, I've written it here, A1 plus A2 is equal to A total. That makes me have to deal with both this area on top and the area on bottom. That seems like more than I necessarily need to work with. Another way to say that is that 2A1 is equal to the total area, right? If each of those is half of it, then twice half of it gives us the total, right? So that's just sort of translating this paragraph into math statements. So another way to say that is A1 equals A total over 2. And I have an expression for A total. So this expression, m cubed over 6n squared divided by 2, will give me m cubed over 12n squared. Okay, so we now have an expression, and remember, m and n are constants that are given in the problem. So we have a number, right? That's a number, whatever m and n are, we have a number now that tells us how big this area should be. That seems like important information. Let's see if we can come up with an expression for this area, for area 1. And here's the part that relates to the area between curves, because notice area 1 is the area between F and G. In other words, let's see, I'm going to actually box this thing because I'm going to want to find that later, I'm imagining. And right now, let's write this down. Area 1 is the area between f of x and g of x, right? And f of x is larger than g of x there. But we need to know where to integrate from. We're integrating from 0, and we're stopping at this point here. Okay? And now I realize I haven't given that point a name, and it turns out that that point is very important. So let's give it a name. Right? I don't know what that number is yet. I don't know if I can know what that number is yet, but I'm just going to give it a name. I can give that the x coordinate at that point, let's just call it lowercase a, which means its y coordinate is g of a, right? Which could be written as a ma. Okay. For our purposes, that means we're putting in little a here. Okay. So let's compute this integral. This is going to be the integral from 0 to a. F of x is mx minus nx squared. G of x is minus little mx dx. We integrate, so I'll have m over 2x squared minus n over 3x cubed minus little m over 2x squared, evaluated from 0 to a. We do some algebra. Again, the 0 terms are going to disappear. I don't need to worry about those. So I'm going to have ma squared over 2. Notice I'm going to put both squared terms together, minus m little ma squared over 2 minus n over 3 a cubed. I can simplify a little bit. I'll get 1/2 m minus little m a squared minus n over 3 a cubed. This is area 1. Right? And we also know that this is equal to this thing we had up here, m cubed over 12n squared. So let's take a moment, let's take a breath and think about what we have. This equation here, 1/2 big M minus little m a squared minus n over 3 a cubed equals m cubed over 12n squared. So since I'm doing this in a general form, M and M are numbers, big M and big M are numbers. So I'm just going to kind of underline that these things are numbers that we know. They're given in the problem. So those aren't variables, right? In the problem, they would actually have values. So those parts would all just be numbers. Notice here, little m, that's the thing we're looking for. That's what we want, right? And then we've also got this other variable a. We don't know a, so that's also an unknown. We have two unknowns in this equation, m and little m and a. Two unknowns in one equation is not enough, right? Whenever you have two unknowns in an equation, x plus y equals 1, there's an infinite number of solutions. I shouldn't say whenever, but typically we'll have an infinite number of solutions, right? So x plus y equals 1, 0 and 1, 1 and 0, 2 and -1, -1 and 2, right? We can go on forever. And so we don't typically have a way to solve equations like this for a single value. So what we can do, though, is solve systems of equations. If I had another equation involving these two, then we might have some hope. So we need to find a relationship between this slope, m, and this point. So let's go back to our graph. Okay. So I've written down some information about this point. A is the point where they intercept, and I know A's y coordinate is g of A, but since it intersects both lines, it also has to be f of A. In other words, this is going to be ma minus na squared, right? Notice what I'm saying here, that this point, which is on both curves, has an x coordinate of a, which means its y coordinate according to g of x has to be ma, and its y coordinate according to f of x has to be big ma minus na squared, which means those two things have to be equal. In other words, it must be the case that ma equals ma minus na squared. Okay? So this is an equation that tells us about the intersection of these two curves. There's one obvious solution. If little a is equal to 0, this equation is true. And notice that is exactly the intersection we have at the origin. Both of these go through the origin. So let's assume a is not 0, because we're looking for the other one. Since a is not 0, I can divide this whole thing by a, and I get m equals m minus na. Here's my second equation with little m and a in it. So now I've got two equations. This equation, I'll box it in red, and this one here. Okay, two equations involving these two unknowns. We might be able to solve them. And since this one's written in terms of little m, let's use the elimination, the substitution method, and take this expression for little m and put it into this equation. Okay, so I'm taking this expression here and putting it into this equation. So let's write that out. So we'll have 1/2 m minus, and now here's where instead of little m, I'm going to substitute m minus na. So I'll get m plus na, since I'm subtracting, a squared minus n over 3a cubed equals m cubed over 12n squared. Okay. So let's do a little solving here. M minus m canceled out. I get 1/2 na a squared minus n over 3a cubed, still equal to m cubed over 12n squared. Let's do a little more solving or simplifying. I'll get n over 2a cubed minus n over 3a cubed equals m cubed over 12n squared. So here we see that same sort of thing we saw a minute ago. I've got 1/2 of na cubed minus 1/3 of na cubed. 1/2 of something minus 1/3 of something gives me 1/6 of that thing. Let's multiply both sides by 6 and divide by n. We get a cubed. Excuse me. Oh, I see. Sorry. I thought I saw a mistake, but I was misreading. Multiply both sides by 6 and divide by n. So this side, this 1/6 and the n will disappear. Here we'll have m cubed over 2n cubed. And we'll take the cube root and we get a is equal to, let's write this as m over n, 2 to the negative 1/3. I don't know the best way to write it. That might be one way to write it. Just means the cube root of 2 in the denominator. Actually, let's just write it that way. Sorry, I'm gonna write this a slightly different way. M over n cube root of 2. Okay, so that gives us the value of a. We need the value of m. So now we have this equation m equals m minus n a. M equals m minus n times, and now I'm just putting in this expression, m over n cube root of 2. The n's cancel, and we end up with this expression m is equal to m minus m over the cube root of 2. If you want, you could factor out the m, 1 minus 1 over the cube root of 2 in either case. And that's it. That is the answer, right? So whatever value of m you have in this problem, this would give you the results, okay? Something interesting has happened. Notice n doesn't even show up. Somehow that didn't matter. We're going to look at a picture in a minute that might help explain that. I haven't actually totally wrapped my head around that yet, but it's the algebra certainly shows it to us, right? The way this worked out, n doesn't show up. But I want to kind of go back for a second and think through our process. So that's the really important part here, I think. It's a tricky problem. It's even a tricky problem just to read, right? And understand what this all means. And so if your first step wasn't drawing a picture, add that to your toolbox, right? When we're talking about functions, graphing functions is this incredibly powerful tool to help us understand what's going on, right? We like to look at things. It helps us organize our thoughts, right? It's all about organizing our thoughts in the right way. Naming things is powerful. One of the biggest lessons of mathematics is how much notation matters, how much writing things the best way you can write them, let's not say the best way, because you never know if you got the best way, but writing things in a useful way, right? Talking about the slope isn't going to help me solve it. Writing the letter m to represent it all of a sudden means I can put it into equations, I can manipulate it, do algebra, all these tricks that we've learned. Here's where we get to apply them. So naming things, introducing notation is how that's often expressed, is a great tool for solving things. You really cannot start to understand something if you haven't given it a name. What else did we do? Writing down things we know. Most of the math we did in the beginning, most of these equations I wrote were just statements from the problem or little ideas like we know how to deal with parabolas, we can find the zeros. So I just started gathering information, right? I often liken it to a detective on a crime scene, right? You walk into a room, some horrible crime has happened, you need to solve it. You don't know what the solve is. You don't know where the clue is going to be. You just start looking around. You start lifting up couch cushions. You start inspecting light switches, whatever detectives do. You start asking neighbors. And a lot of those leads don't go anywhere, right? So it's perfectly fine if one of the thoughts you had here was something like, I don't know what you might have done. There's other things you could have thought to do. It didn't go anywhere, and that's fine. It means you go, all right, I'm not looking in that closet again. I'm going to try something else. And it's very true that although when I did this, I've solved this before, the first time I solved it, I didn't know what the steps were going to be. I didn't know I was going to need to use this point here. Maybe I could have guessed that, maybe I didn't. I started thinking about areas, I got a bunch of stuff and realized I had this extra variable, this letter A. And so then I had to go back and deal with it, right? And another thing we did a lot of in here is translating statements into mathematical equations. The statement that this area 1 is half the total area became this mathematical statement right here, right? This is the statement that area 1 is half the value of area 2, right? So twice the area 1 is equal to the total area, right? And translating those statements meant, right, then translating area into integrals, we ended up with a nice equation, right? And that's what we want, because at the end we needed little m to be equal to something. So we had to introduce some equations. Okay, let's take a look at the graph of this to give us another insight into what's happening. Let's see. All right. Whoops, sorry, that's the wrong thing. Let me try again. There we go. All right, so here's a picture of a possible version of this. So notice what I have. I've actually put in these constants m and m that I can change, right? That'll change this parabola. And so you can look up here, f of x is the parabola as stated. And for g of x, that's the line. I used what we just solved, what we just found for the value of the slope and put it into the slope formula. So that line always adjusts. Notice as I change m, I'm changing the other 0 of this parabola and the slope of the line is changing. Notice as I change n, the parabola changes in a different way, so that line doesn't have to change to still be splitting the area. Oh yeah, and notice here, these two boxes, the top box is the total area under the purple curve, but in this, the region we were looking for, and this second integral I have here is the half area in the top half. And you'll see that as I shift these numbers, they always remain, right? The bottom one is always half the top one. Okay. In other words, that orange area, as I move n or m, according to what we found, is always half of the total area, or the orange red on top is equal to the lighter orange on the bottom, right? So it's a pretty interesting, it's still surprising to me that n didn't turn out to matter. The way it changes the parabola, it changes it in a way that the line doesn't have to shift to stay in that equal ratio of areas, whereas changing m does make it have to shift, right? As m gets smaller, it gets smaller and smaller. All right, in any case, that's the end of that one. I hope that helps. I know it's a complicated problem, but the interesting problems are complicated typically. This one takes patience. It takes a lot of notes and organizing. Oops, you can't see that when it's not by my face, right? So this is several attempts. I have scratch paper, right? It didn't look that neat and clear when I first wrote it down. It took me a couple tries because things got sloppy and I just had to reorganize. Don't be scared to start over, reorganize, name better, all that kind of stuff. Okay, that's enough for this one. Thanks, everybody. I will see you next time.